Let's talk about a super powerful tool that helps us see clearly, even when we're surrounded by messy, noisy data. It's an incredible algorithm that's kind of hiding in plain sight, working its magic in the background of so much of our modern tech.
Okay, so let's kick things off with a question that gets right to the heart of a huge problem: uncertainty. I mean, how do systems make any sense of imperfect information? You've seen it, right? You look at your phone's GPS, and the raw signal is just bouncing all over the place. So, how does it pinpoint your location? Well, the answer lies in a really brilliant piece of mathematics.
And to find that answer, we actually have to jump in a time machine. We're going to go all the way back to the space race, a time when knowing your exact location was quite literally a matter of life and death.
So the story starts in 1960 with a guy named Rudolf Kalman. But his idea almost immediately got the ultimate baptism by fire, navigating the Apollo missions to the moon. I mean, talk about high stakes. From there, its use just exploded. Now it's in everything from self-driving cars and robotics to economic forecasting.
Now, this is the crucial point. You have to get this. In the real world, perfect information just doesn't exist. And the genius of the Kalman filter is that it doesn't need it. It works its magic by blending two imperfect things: a guess from a perfect theoretical model and a flawed, messy measurement from the real world. And the result? It's an estimate that is way more accurate than either of those two things on their own.
Okay, so let's really dive into that core idea. To get our heads around it, we're going to use a super simple analogy, just tracking one single car as it drives down a road.
No matter how complex the application gets, whether it's a spaceship or your phone, the whole process boils down to this really elegant two-step cycle that just repeats over and over, getting better with every single loop. This is where the magic happens. The first step is the prediction. So using what we know about physics, speed, acceleration, all that good stuff, we make an educated guess. We say, okay, the car should be right here. Then comes the correction. We take a reading from a real sensor, like a GPS, but we know it's not perfect. It's noisy. And we use that messy real-world data to nudge our initial prediction to correct it. And this little loop is just relentless. Every time we make a correction, that new, better estimate becomes the starting point for the next prediction. It's a constant feedback process that lets the filter just zero in on the true position, shaving off more and more of the noise with every single cycle. So let's peek under the hood for a second and see how this simple idea is built on a really solid mathematical foundation. But hey, don't worry, we're not going to get lost in the weeds. Just understanding the basic structure is all we need. Before we even glance at the equations, it's really important to know the ground rules. The Kalman filter really shines when a system's behavior can be described with linear equations, and when all the noise, both in how the system moves and in our measurements, follows that classic bell curve shape, what we call a Gaussian distribution. Okay, this first equation, this is basically our prediction step, just dressed up in math clothes. All it's saying is that the car's true position now is based on where it was a moment ago, plus any controls we're using, like hitting the gas, and a little bit of random noise. This is our physics model in action. And then we have this second equation. This is our correction step. It says that the measurement we actually see is related to the car's true state, but it's been corrupted by some measurement noise. This is the key that lets us take that messy observation and use it to update our prediction. All right, so we've been focused on just one car. Let's zoom way, way out and see how this amazing concept applies to a much bigger, much more complex modern problem: managing the traffic for an entire city. And this is where the filter's power really scales up beautifully. We're not tracking a simple thing like position anymore. The state is now the whole dynamic, chaotic, ever-changing condition of the entire traffic network. So what does that state actually look like? Well, it's a whole collection of key variables. The filter is constantly sifting through tons of noisy data from road sensors and cameras to give us a clean, reliable, real-time picture of things like vehicle density, average speed, and even how long the lines are at intersections. And this quote, this just nails why the filter is so critical for modern AI systems. Think about it. A smart traffic system needs a crystal clear picture of reality, an accurate state to make good decisions. If you feed it garbage, you're going to get garbage decisions. The Kalman filter is that crucial step that provides the clean, reliable input. So, let's bring it all home. What's the big takeaway from this incredible algorithm? If you remember anything, remember these three things. First, the Kalman filter is an absolute master of estimation. Second, it fully embraces imperfection, taking a clean guess and blending it with messy reality. And third, it produces the best possible answer through its simple, relentless cycle of predicting and then correcting. And that leaves us with a final thought, doesn't it? The Kalman filter really teaches us a powerful way of thinking. Take a model of how you think the world works, constantly test it against messy reality, and then update your beliefs. It kind of makes you wonder, if we can do this for a spaceship or a city's traffic, what kind of cognitive biases or emotional noise could we learn to filter from our own day-to-day judgments?